Okay, let's get started. So now that we've covered a lot in latency, we're going to switch gears a little bit and look at more complicated relationships. We were looking at the latency-reliability relationship. Now what happens if you actually look at voltage in addition to that? And I think things are going to get more complicated from here in DRAM. We need to understand more. I don't think we understand enough, but there's more to do. But basically, the reason we started looking at this was the power consumption in DRAM, and this is the pictorial view of what I told you a couple of days ago. More than 40% of the system power is documented to be spent in DRAM, and these are papers that analyze these. This is IBM Power 8, and this is a GPU. Existing DRAM designs actually helped reduce DRAM power, but they lower supply voltage relatively conservatively. And reducing supply voltage is good because power has a quadratic relationship with voltage, as you can see. And DDR3L, for example, its low voltage reduces voltage from 1.5 volts to 1.35 volts, about 10%, which is not bad, but even that is conservative. And LPDDR4 employs low power I/O interface with 1.2 volts. In this case, we weren't able to test LPDDR4s with this infrastructure, so I'm going to give you results with these. So the key question that we wanted to answer was, can we reduce DRAM power and energy by further reducing supply voltage? So we wanted to understand and characterize the various characteristics of DRAM under reduced voltage, especially how does voltage interact with latency and reliability, and develop a mechanism that reduces DRAM energy by lowering voltage while keeping performance loss within a target. I'm going to talk about this mechanism. And I think there's more to be done in this area also. So there are several key questions. How does reducing voltage affect reliability, meaning errors? How does reducing voltage affect DRAM latency? Or how can you compensate for reduced voltage? How do we design a new DRAM energy reduction mechanism? So for this, we actually built a new infrastructure. You can read the paper for more details. Basically, adjust the supply voltage to every chip on the same module over here. We extended our FPGA-based infrastructure such that we can adjust supply voltage to different DRAM modules and schedule DRAM commands to DRAM modules and to actually change the voltage. Okay, so this is what we've tested. 124 DDR3L low voltage chips, and this is the baseline voltage, and these are the different parameters that you can see. Basically, we iteratively read every bit in each 4 gigabit chip under a wide range of supply voltage values. This is the lowest that we could go to 1 volt. And let's take a look at the relationship that we observed between supply voltage and the fraction of cache lines with errors. This is the percentage of cache lines that have errors. Nominal voltage is over here, and these are 3 different vendors. Clearly, as you reduce the voltage, you would expect the fraction of cache lines that you see errors in to increase. But what is the shape of the curve? Okay, so shape of the curve is different for different vendors. As you can see, this vendor doesn't have a lot of margin, and you get errors very quickly over here when you reduce the voltage to 1.275. Whereas this vendor, these 2 vendors actually have a lot of margin, and you can go down to 1.15 volts over here until you start getting errors. And these, you can see there's variation also in the error rate across different modules. So basically, this is the minimum voltage that you can operate at without errors, and that's dependent on the manufacturer. Clearly, there's a lot of variation between manufacturers and between the chips. And you see the errors that are induced by reduced voltage operation. And clearly, reducing the voltage below Vmin causes an increasing number of errors. And at some point, you get things that are rife with errors. So this is expected, I think, but there's a lot of heterogeneity here also. So we actually built detailed circuit simulation models. It's always good to do circuit simulation plus real experiments and try to match them somehow. And we actually release our circuit simulators too that are online. They're relatively simple. They're not extremely sophisticated. But this is what you would expect between voltage and latency based on our circuit model. This is the activate latency, and this is the pre-charge latency. This is the nominal voltage. As you reduce the voltage, the reliable operation latency is expected to go up. This is the latency required for you to use for activation and pre-charge such that you don't get errors based on our circuit model. Which means that if you're operating at low voltage, you need to wait longer such that you don't get errors. And this is also obvious, hopefully, right? That makes sense. And we wanted to see this curve in real life also. Does this curve that we get in simulation, circuit simulation, match what we observe in real life? Because in real life, we can do this experiment. Once we reduce the supply voltage, we can also increase the latency to see what is the latency that we need such that we don't get errors. And this is the real life, basically. This is same curve, supply voltage, and measured minimum activation latency. The other latency pre-charge is very similar. And what this shows is, this is the measured minimum latency that does not cause errors in DRAM modules. And this is a density plot, basically. This is 100% of the modules don't see errors if you actually have supply voltage, 1.35 volts, and if you use an activation latency of 10 nanoseconds. And that's true until here. So this is clearly one of the manufacturers, not the worst manufacturer, as you can see. So basically, 100% of the modules are operational at 10 nanoseconds activate latency until 1 point, whatever that voltage level is. And when you get to 1.1 volts, you need to increase the latency by about 2.5 nanoseconds for 10% of the modules. And still, all of the modules are operational. And when you get to 1.075 volts, 50% of the modules still operate at 10 nanosecond latency, but for 40% of the modules, you need to increase the latency by 2.5 nanoseconds. And some modules actually don't operate correctly, regardless of whatever latency. And as you go over here, basically, you can see that the shape of the curve is very similar to what we've seen. The shape of the curve looks like this over here, and that's what we kind of observe over here. And this is the distribution of latency in the total population. And as you can see, this is the lower bound of latency. So we have this margin over here because we cannot change the latency at a finer granularity than 2.5 nanoseconds. That's limited by the frequency of our FPGA, basically. OK. So again, this is obvious, but it's experimentally validated as well. DRAM requires longer latency to access data without errors at lower voltage. Yes?
In the SPI simulation, the previous slide, that was simulating a single cell?
That was simulating, I think we were simulating a subarray, actually. A small subarray. Yes. So it's not taking into account all of the effects in the chip, for sure.
How much it depends on the technology of the DRAM and the manufacturer itself, which fab it was used.
Yeah.
Etc.
So we don't know the fabs. We cannot affect that. And we didn't test different technologies. But I expect this shape of the curve will be similar for different technologies, but the points may be different, like where you are exactly increasing. And the distribution may be different also. OK.
You have one that, like,
Exactly, yeah.
but some are...
Exactly, yeah. I mean, it's very hard to exactly know what it is that's causing it. And we haven't done enough studies to actually reverse engineer what's happening underneath. OK, so there's spatial locality of errors here also. For example, some banks are actually much worse, whereas some other banks have no errors. This is interesting. Basically, this is the probability of row having greater than or equal to 1 bit error. As you can see, there are some banks in the same chip that have no errors, but some banks have errors. And even within the bank, you have not all rows that have errors. Some rows have errors. So this is somehow related to the voltage distribution. We don't know exactly. We don't know exactly how the voltage is supplied internally in the DRAM chip, but you could exploit this if you know this profile. So errors concentrate in certain regions in this case. And these are our key observations, basically. This is, I already said, voltage-induced errors increase as voltage reduces further below Vmin. Errors exhibit spatial locality, and increasing the latency of DRAM operations mitigates lower voltage-induced errors. And this is actually very fundamental, I think. So you can trade off between voltage and latency, which means that energy and latency, right? And we didn't really examine ECC in this case also, so there's also that aspect, right? You could certainly overcome some of these errors with ECC. I don't know if that's a good idea. This is an area that we don't understand enough, in my opinion, yet. We understand a lot more at refresh. We understand a little bit less in latency. We understand even less in voltage. But there is some understanding. OK, so now that you know some things, and there's a lot more data in the paper that I'm not covering here. I don't want to bore you with a lot of data, but you can always read the paper. We wanted to exploit the trade-off between voltage and latency to reduce energy consumption. Our goal was to actually do something different, but based on the characteristics that we've seen, this is what we could do. The approach is to reduce DRAM voltage reliably, and you have performance loss due to increased latency at lower voltage. We compensate for the reliability loss by increasing the latency, exploiting that trade-off that we just saw. And this is the improvement over nominal voltage. If you actually reduce supply voltage this way, you save DRAM power, but your performance reduces because you're increasing the latency. Right? So this may not be a good trade-off, as you can see. Right? You don't want to always reduce your supply voltage to gain power savings because that's reducing your performance. Okay, so how do you achieve a good power savings while limiting the performance loss? 20% is not an acceptable performance loss for most workloads. And that's, yeah.
You're talking a lot on power, but as a matter of fact, you may want to look at energy in there.
That's right, yes.
So the energy saving is much less.
Exactly, the energy saving is much less because you're losing so much performance. Yeah, we're going to look at energy over here. This is just to motivate, basically. But I agree, energy saving is much less over here. I mean, here it may be okay. But the power saving is lower also.
You try doing a similar thing, but instead of increasing latency, adding strengthening the ECC.
Yes, so that's something we did not explore. But I think that's a very good area to explore.
Capacity and retain energy in that sense.
Mm-hmm.
You gain by dropping the voltage.
Yeah.
Gain energy by having more cells.
Yes.
You may end up winning.
Yeah, I agree with you. And there's a lot of work actually on chip caches doing something similar, reducing the voltage significantly and adding ECC. But we haven't done it over here. There's more to do in this area for sure. Okay, so this is the idea of the mechanism. I'm not perfectly satisfied with this because it's going to use some regression model that I don't necessarily like to build the model, but that's okay. We'll do that. So basically, users specify some performance loss target, and the system selects the minimum DRAM voltage without violating that target. That's the key idea. So the key question is, how do we predict performance loss due to increased latency under low DRAM voltage? And this is where the regression model comes in. Basically, we build a model to predict performance. You take application's characteristics and DRAM voltage, and the model gives you a predicted performance loss based on the latency that you need at that voltage, right? And based on that performance loss, you select and the target that you actually want to achieve for the application. You select a minimum voltage, and that's your final voltage. That's the idea. So how do you actually model this application characteristics? Basically, we use memory intensity, frequency of last level cache misses, because that definitely affects. That's definitely affected by the memory latency, and that affects the latency of performance of the application. And we also use memory stall time, amount of memory requests. This is to measure basically the parallelism that an application has, more or less. But we could always have better models. And to handle multiple applications, we predict the performance loss for each application, and we're conservative, meaning that we select the minimum voltage that satisfies the performance target for all applications. So we had actually done some work in the past. This is the work that we've done collaboratively with Intel, proposing dynamic voltage and frequency scaling with the infrastructure that we had. Basically, the idea is to dynamically scale voltage and frequency of the entire DRAM based on bandwidth demand. The problem is if you lower voltage on the peripheral circuitry, you actually decrease the channel frequency. So this is basically, if you look at the peripheral circuitry, we were actually reducing the voltage over here. So everything was low voltage. As a result, you were actually affecting the bandwidth. And as a result, that's why we were actually, based on the bandwidth demand, we were deciding what voltage to use. We're going to compare to this work. I think this was the state of the art until Voltron. Basically, Voltron's idea is to reduce the voltage to only the DRAM array without changing the voltage to the peripheral circuitry. So you somehow keep this unchanged such that you don't affect your bandwidth, but you change the voltage over here. I think this makes a lot of sense. You don't want your energy to be coupled with your bandwidth. Okay, so the next idea is to exploit the spatial locality of errors that I've shown you. Increase the latency only for those DRAM banks that observe errors under low voltage. The benefit is, of course, when you're accessing these other banks, you can access with low latency and low voltage, but only these banks that are affected by low voltage in a bad way, you access them with high latency. So that's the idea. Oh, not bit line based, you mean? Yeah. So I have two answers for that. One is this is what we figured it out, and the second is we didn't analyze as much further. So it could be actually finer grain, but we didn't get there. Maybe there's a finer grain thing. My feeling is it could be subarray based, but also I think there's something that we don't fully understand. There's voltage that's supplied to the bank and somehow gets distributed to the subarrays. We don't fully understand how that gets distributed at this point. We understand the latency components better.
I think the graph that you had showed that.
It's bank-based, right? Yes, that's true, but I mean, we didn't really go to the next step and analyze, oh, is it really subarray-based, and what is the variation over there? So it could be subarray-based also.
But the banks that were sort of, how do you say, stained,
Sure.
were quite stained all over.
That's true, yes. So it's definitely bank-based, but there could be even finer granularity that we don't exploit. Yes, so that's the idea. Of course, bank-based is easier to exploit, right, than subarray-based. It's a coarser granularity. So yeah, basically we use RAM later again. And the source code of this is online also. And we compare to our prior work, MEMDVFS, we call it, which does dynamic DRAM frequency and voltage scaling, and scales based on the memory bandwidth consumption. So it doesn't really look at the performance target like this. Okay, so this is basically what you get. This is the total energy savings in CPU and DRAM. Basically, if your memory intensity is low, with memory DVFS, you save some energy, but not as much as what we do. And if your memory intensity is high, the previous work doesn't save energy because it really reduces voltage and frequency when your memory bandwidth demand is low. So it cannot reduce it over here, whereas Voltron actually saves significant energy. And there's a lot of analysis in the paper that you can see. And this is the performance target. Of course, you meet your performance target based on your specification of the performance target. Our specification was we don't want to lose performance by more than 5% in any application. And I think in the end, we saw that we don't lose performance by more than 3.2%. There should be a maximum over here, which I don't show, but in the paper, the maximum is reported. In any application, we don't lose more than 3.2%. And the average loss is this, although you could argue that average loss doesn't matter if you're trying to meet a target, right? So that satisfies the requirements. But still, I'm not satisfied because it's based on a regression model that is really based on profiling applications. I think there should be a better model for this. But this, according to our simulations, this works. Any questions? There's a lot more data in the paper that I'm not discussing. The key ideas are hopefully clear. So I think now the advantage is this gives you another level of flexibility. You can trade off between voltage and latency to improve energy and performance. And it can exploit the high voltage margin present in DRAM. But of course, the disadvantage is it requires finding the reliable operating voltage and its relationship with latency for each chip, which means that you have a higher testing cost now. I think there's a lot more to understand. This is the state of the art in terms of DRAM voltage, latency, reliability characteristics. If you're interested, I'd be happy to talk. There's more to do in this area for sure. Any questions? Yes, please.
How long does it take to test a single bit?
That's a good question. It takes a lot, actually. I don't have a number off the top of my head, but you can do the calculation.
Hours, days?
It could be hours, yes. It's easily hours, depending on the test you do, like how many voltage levels you want to test, how many latency levels you want to test. It could easily be days, actually. It usually takes days.
And you're saying it's pretty much stable for months? Like the results? For how long?
Well, I think the results are stable for, once you determine the reliable latency and add some margin to it, then they're stable for, we cannot test forever, of course, but for months we see that the results are, you don't get errors.
So bottom line, the cost is a few hours per several months.
Maybe, yeah. I don't know. I think you can optimize these. We didn't really do the testing with production testing in mind, right? We did the testing for our understanding at this point. If you really want to optimize that testing, you might be able to do better. Yeah.
Since it's all based, you cannot rely on ECC to discover errors later in the game or something. You have to be right.
Exactly. In this case, you have to be right. But I think you can take it to the next step, and if you have ECC, you can try to do it dynamically, right? All of these optimizations. I think all of these optimizations are better if they're dynamic somehow. That way, you get rid of all of that earlier testing cost, and you do online profiling. I think we know that very well with refresh. That's what I meant by refresh. We know very well at this point. We always don't know enough, of course. There's stuff that we don't know, but we know that better than latency. We know latency better than voltage. We're just exploring these now. Okay. I'll pose this question. We didn't look at this, but I think if you can sacrifice reliability of some data to access it with even lower latency, that opens up even more opportunities, right? Here, we're not giving up reliability, right? we're basically saying you want to be reliable, and period. But there's a lot of data where you don't necessarily need to be reliable, as we've discussed in heterogeneous reliability memory. If you actually know that, and if you map your data such that you can access it with lower latency and you get errors in that, and you know that that's okay, there's a whole new world of opportunities over here that we didn't really exploit yet. Okay, so let me switch gears a little bit. I'll cover a couple of other works, and I think we'll be done with the latency part by the break. So I'm going to talk about this because this is fun. While we were actually playing with latency reliability trade-off, we actually discovered that you could use DRAM as a physical unclonable function generator. So what is that? Basically, we want a way to ensure that a system's components are not compromised. And physical unclonable functions were proposed in early 2000s. It's a function that you evaluate on a device to generate a signature unique to that device. There are other use cases, but I'm going to motivate it with this use case. And you refer to this unique signature as a puff response. It's called a puff, basically. It's often used in a challenge response protocol, CRP. And it usually works like this. You have a trusted device that wants to authenticate some other remote device, let's say, to basically to start a communication. So it basically challenges the device with some input X. And device evaluates a physical unclonable function and gives the response X corresponding to X. And the trusted device checks that response based on some earlier registered response, right? And if that response matches, then the device is authenticated, and now you can establish communication with it because you know that this device was not compromised in some way. Somebody didn't take that device and replace it with some other device that's malicious, right? So that's the idea. That's one way of using a puff. And the motivation was we want a runtime accessible puff. It should be evaluated quickly with minimal impact on concurrent applications because this evaluation is done while this device is doing other stuff, right? You can protect against attacks that swap system components with malicious parts, and I think this is becoming a much bigger issue going forward. I think it's even making the popular news these days, right? And I think we found out, at least maybe somewhat randomly, that DRAM is a promising substrate for evaluating puffs because it's ubiquitous in modern systems. Basically, DRAM is everywhere. If you can use DRAM and you can use its inherent characteristics to generate these puff responses, you don't necessarily need a dedicated circuit for this. And people have looked at DRAM puffs. What they've done is people have found out that DRAM retention times, if you change the refresh interval, lead to a unique signature for the device. Unfortunately, retention time is something that leads to errors if you actually increase the refresh rate for a very long time, right? As a result, existing DRAM puffs are actually slow, and they get exponentially slower at lower temperatures. I'm going to show you some data based on this, because we can also change the refresh rate in our device, so we compare to that sort of puffs. Latencies are much better to generate the puffs. So basically, according to our observations in many devices, and there's a lot more statistical analyses that we do in the paper. I'm not going to go into the statistics as much here. Latency failures come from accessing DRAM with reduced timing parameters. And a cell's latency failure probability is determined by a random process variation. And latency failure patterns are repeatable and unique to the device. So we're going to exploit that. The key idea is the probability, the latency failure probability, meaning that when you access the cell with a reduced latency, the probability of failure is inherently related to that random process variation. And you can provide repeatable and unique device signatures using latency error patterns. So assume these are random process variation. Some of them are high chance to fail with reduced TRCD, and some cells have low chance to fail with reduced TRCD. And the key idea is to compose a puff response using the DRAM cells that fail with a high probability. That's the idea. How you do that exactly, you should take a look at the paper. I think this is kind of obvious. Basically, this is what happens when you actually read a DRAM cell activate. During an activation, sense amplifier gets enabled here, and there's a ready-to-access voltage level. Because of process variation during manufacturing, cells have unique characteristics, and we're going to exploit that characteristic. So if you actually move the TRCD over here, weaker cells have a higher probability to fail, and here you get a unique signature, basically, if you move the TRCD at a good point over here. Okay, so hopefully that's clear. So you need to, of course, find some regions that are good. Yes?
About the dependence on temperature, you want to be robust.
Yes. So actually, the latency puffs are not dependent on temperature. That's the good part.
So the probability of failure is independent of operating conditions?
Yeah. We actually analyzed that in the paper. I don't have the slides over here. But retention puffs are very much dependent on temperature. But latency is not as much, at least these latency puffs, if you select the regions well, you're much less dependent on temperature. There is some dependence, but it's definitely not exponential, and it's much, much less. Yeah, it's in the paper, yes. There's a lot of analysis. I'd be happy to talk. You can take a look at the paper. Yeah, sure. Okay, so basically, we said this already. The latency area patterns satisfy puff requirements. There are a bunch of requirements for a puff that the paper actually talks about also, and you can take a look at that also. I'm not going to go through that. And basically, the latency, the time to generate the puffs is about 88.2 milliseconds. So you get this puff response in 88.2 milliseconds. So let's take a look at this evaluation latency. This is temperature over here. Actually, I have this over here also, interestingly. But the paper has more analysis in terms of the robustness of the puff to the temperature. Here we look at the latency. And this is the evaluation time, how long it takes to get the puff response. And this is the DRAM latency puff. It turns out it's constant latency, because latencies are like that. And this is the DRAM retention puff. So you need how big of a memory segment you choose affects your latency. This is with manufacturer A. It takes some time to generate the puff because your retention time is very long. So you need to wait for a long time for the cells to drain charge to be able to get some random values in the cells. So you can see the speed up is very high over here, and the speed up is still pretty high over here at high temperatures. But at low temperatures, the latency puff is better. And this is, if you increase the memory segments, you actually do better because the probability that you get more cells failing increases as you look at a bigger segment. But this is still higher. And as you increase the memory segment to be 64 megabytes, that's even better for the retention puff. But the speed of the latency puff is still an order of magnitude faster. And manufacturer B has this property. And if you look at manufacturer C, you have basically similar curves because retention is very fundamental, right? They all follow very similar curves, give or take some distance differences. Okay, so basically we have a puff that's fast and constant latency. And on average, it's about 100 to 800 times faster than the previous DRAM puff with the same capacity overhead, assuming you equalize for the capacity overhead, 64, I guess, kilobytes over here. Okay, there are a bunch of other results that you can take a look in the paper. I think this is really important. It meets the basic requirements for an effective puff. And there's more analysis on the devices of 3 major manufacturers. And these are all LPDDR4 devices, the evaluation time of a puff, and other stuff, basically. I'm not going to go into the detail over here. So I think this is really interesting because if you have an infrastructure like this, you can also come up with mechanisms like this. We actually have something under review right now on random number generation, which is very similar, but random numbers, here it's a puff. Random numbers need to satisfy different requirements. And we show that you can use the latency, reduce the latency, get errors, and it turns out it's a true random number generator. It's a very high throughput true random number generator, so you don't really need another random number generator. Of course, you write this paper, send it to the reviewers, and what is the first thing the reviewer says? It's not what?
It's not random.
No, actually, they don't say that. It's random because we proved that it's random. This is the fun part. Who needs a better random number generator? Really, right? Yeah. Exactly, that's the response you get. Who needs a better random number generator, right? I think that's the progress we want to make in science. Anyway, this is, if you get reviews like this, don't be discouraged. Everybody gets reviews like this. Somehow there's a trend for backwardness, I think, in science that you should read the structure of scientific revolutions, basically. I think I'll leave it at that, but yeah, who needs a better processor, right? If we had that mentality in really pushing forward with science, then we would be staying in the Stone Age, probably. Say it again? So proving is, okay, maybe as it says, so there's these standardized tests, the NIST tests, and it passes all the NIST tests. And I think that's the really, that's as best as we can prove today in the methodologies that we know. Yes. But it's a very high throughput random number generator. It's not as high throughput as the ASICs that you can build, but with DRAM, without modifying pretty much anything, except for the memory controller a little bit, you can get it for free, almost. Yes?
Could you use something like the row hammer attack to discover the signature
Mm-hmm.
in a path and then basically clone it?
Basically what?
Clone it.
Clone it, I see. That's actually interesting. I don't know. I haven't thought about it. Yeah, I haven't thought about it. So if you do the row hammer, then you will need to somehow, yeah, I don't know how you would do that. But I think people have looked at row hammer as as puffs also, but I haven't. I don't remember. So there is some relationship over there, but maybe we can take it offline, and I'd like to understand what you mean exactly. Yes.
Isn't there a problem with a puff that you can detach from your system and put in another system? Like if you can take your DIMM, put it in another system, then you can mimic the puff, like you transfer the puff.
Yeah, you could, but in another system, it needs to be registered somehow, right? So that you may not be able to authenticate it, because these are different. You get unique signatures.
It's even for the system, not just the DRAM chip.
Yeah, exactly. Yeah. Yeah. Okay. Okay, so if you're interested, you can read this. So we have some work on reducing refresh latency, which I'm not going to go into, but you can take a look at this paper. The idea is actually relatively similar to partial restoration. I'm going to talk a little bit about reducing memory latency by exploiting memory access patterns. Let's see if we can cover everything. So this is, I think this was brought up earlier. In this case, we're not going to do any modifications to existing DRAM system. We wanted to reduce access latency that way. And the observations are simple. A highly charged DRAM row can be accessed with low latency because it has highly charged. And a row's charge is restored when the row is accessed. And a recently accessed row is likely to be accessed again because of bank conflicts. We call this row-level temporal locality. And the key idea, if you have these observations, is you track recently accessed DRAM rows and use lower timing parameters if such rows are accessed again. And we call this the ChargeCache. It has low cost and no modifications to the DRAM. You just need a table in the memory controller. And you get high performance, basically, and lower DRAM energy at the same time. And let's take a look at why this is happening. I've shown you this picture before. This is a cell with some charge, sense amplifier with VDD over 2. You activate, and the sense amplifier starts sensing, and it kicks in after some point. It basically restores the charge. The cell becomes ready to access over here, so you can read and write over here. But of course, now you know that you can reduce the write latency, but that's a different observation. And this is the ready to pre-charge level. Right. And then you can pre-charge it. So these are the two access latencies. So let's start with this. This is a cell that's somewhat charged, right? Its charge level is higher than the ready-to-access level. What if we started with a cell that had a lot of charge to begin with? Everything becomes earlier. So basically, things shift to the left. And we're going to exploit that shift to the left to reduce TRCD and TRAS latencies. So the first observation, a highly charged DRAM row can be accessed with low latency. And you knew that before. And these are some results that are in the paper. Then the key question, next question is, how does the row become highly charged? Well, DRAM cells lose charge over time. There are two ways of restoring a row's charge. You need to refresh it. Well, you have to refresh it. That's one way of restoring the charge, which means that if you're accessing the cell over here, it has a lot of charge, you can use a lower latency. If you're accessing the cell over here, it has low charge, so you should access it with long latency. Right? And also there's accesses in between, so accesses also restore the charge. So if you've just recently accessed the cell, you can access it with low latency. And that's the idea over here. A row's charge is restored when the row is accessed or refreshed. Then the next question is, how likely is a recently accessed row to be accessed again? You could also say, how likely is a recently refreshed row to be accessed? But refresh is asynchronous to accesses, so there is no correlation between those actually. But there is a huge correlation between accesses and accesses to the same row. Basically, because of bank conflicts, a recently accessed DRAM row is likely to be accessed again. We define this metric called T, row level temporal locality, fraction over those that are accessed within time T after their previous access. And let's take a look at those fraction of accesses. Basically, if you choose T equals 8 milliseconds, more than about 86% of the rows are accessed again within 8 milliseconds after their previous access. This happens because of bank conflicts, basically. And this one, somehow it didn't work. We can take a look. And if this becomes higher, if you actually have a lot of contention in the memory system. Basically, if you have 8 core workloads, they're all banging on the memory bus. They're all having bank conflicts with each other. So the probability of accessing a row within 8 milliseconds after its previous access is 97%, assuming you access the row again. If you don't access the row again, then of course this doesn't contribute over here. That's why this number is very high. So there's very high row level temporal locality. And the key idea as a result is to track recently accessed DRAM rows and use lower timing parameters if such rows are accessed again. And you can do this completely in the memory controller. The memory controller basically keeps track of requests. Let's say the request is row A. Is it in the charge cache, meaning is it recently accessed? No. Then use default activation latency, default timings. Okay, now you get another access to row D. It's not in the charge cache, which means that you use default timings. This is to the same bank. Now you get another access to A. You need to activate it again. Is it in the charge cache? It is in the charge cache, meaning that you recently accessed it within last 8 milliseconds, so you can now use the lower activate latency for that. And that's the idea. And if time passes, if more than 8 milliseconds pass, you can clear the charge cache because you don't want the values over here to be stale. And that's the idea. So we evaluate it. You can take a look at the paper. It's very low cost in terms of area and power in the memory controller. And the methodology is, I mean, as usual, we use our simulator. Okay, you can read that more detail. So this is the performance improvement that you get. NUAT is actually some previous work that proposed to reduce the access latency if a row is accessed right after it's refreshed. So you get some performance benefit with NUAT. ChargeCache is actually better because it's exploiting this row-level temporal locality. There's no correlation between a refresh and an access, as I said. That's why you get very little improvement with NUAT. And you can actually combine the ideas. And LLDRAM is the upper bound. Basically, you get close to the upper bound in most applications. You get far away from the upper bound, meaning you access all of the DRAM rows with the lower timing parameters that we use. So in some of these cases, we don't get close to the upper bound because ChargeCache is not large enough. Okay, so you can improve single core performance, and you can also improve multi-core performance, as you see over here. Okay, and the energy savings are also significant. I'm going through this relatively quickly because hopefully the idea is very clear. And this is the paper. Yes? So the energy saving mainly comes from, there are two reasons. One is you're not driving the interconnects long. That's reducing the energy. But also, you're improving performance, right? There are two reasons. I don't know which one's higher. Well, you improve performance. Your average power goes up, but energy goes down. Yeah, average power, I agree, definitely. That goes up. Yes?
What about the workload that you're using? It looks like this is a spec
Yeah.
2000, it is not even 2006.
This is 2006, yeah.
2006.
Yeah. It's not 2017, though, yeah.
What happens if you choose much larger systems and databases
Yeah.
or workload?
Yeah, I mean, I expect that to be closer to, basically, it depends on the charge cache size. For example, some workloads, it require a bigger charge cache size, and we don't have a large enough charge cache to cover. So you can actually get to this high speed up, closer to the high speed up by having a larger charge cache. So I think the behavior will be similar. As long as you have bank conflicts and this row level temporal locality, you will get benefits, but you may need to increase the size of your charge cache.
Because the footprint of most of this application is quite limited.
Yeah. Yeah, that's true. That's true. I mean, we see this even in these applications, right? If you choose a 32 entry charge cache size, that's not enough. You need to go up to, let's say, 256. Right? Yeah. Okay. Let's see. Any questions?
By the way, the 8 cores, what benchmark you're using? Just the
Multi-programmed, yes. Yeah. Mm-hmm.
Same program or?
No, it's mixed. It's heterogeneous, basically. Yes. Yeah, because activation latency. Yeah, I think that's a very good point. Whenever you reduce the activation latency, the probability of row hammer increases. But hopefully you have some other protection for row hammer. I'll use the same answer that I gave him with the timing. We know, I think, a better protection for row hammer, but yes. Okay, so this is the last work that is actually going to be presented at Micro, but I'm not going to talk about this. It's going to be too much latency. Any questions? Maybe I'll start the next session concluding low latency memory, because I want to talk about power before I start the next session. So this is probably a good place to stop, and you can think of questions during the break also. Okay. See you after the